We're going to take a look at vertical movement of water in the ocean, that is, upwellings and downwellings in the ocean. So most of the motion of water in the surface is lateral motion, horizontal motion, driven by the winds. So the winds, the easterlies and westerlies, they drive surface circuits in the ocean, forming the gyres, the 5 gyres of the ocean, and the the Antarctic circumpolar current. But sometimes the wind can move water horizontally so that it instigates the vertical motion of water. Whenever water moves upward towards the surface, we call that upwelling. And upwellings bring cold, nutrient-rich water to the surface. And whenever water moves from the surface down, we call that a downwelling. And downwellings are important because they take oxygen-rich water from the surface down to the larger depths. Well, one place in which upwelling and downwelling occurs is along the coastlines. So, for example, if we look at South Africa, we can see that the temperature of the water on the east coast and the west coast of South Africa, is very different. So we can see there is, 26 degrees centigrade on one side, and we have 19 degrees centigrade on the other side. So it's very different. Well, part of this is because the east coast of Africa has a western boundary current, which is bringing warm water from low latitude to high latitude, and the west coast of Africa has a eastern boundary current, which is taking cold water from high latitude to low latitude. But also, what's happening here is that the easterly winds are blowing right here. So they're blowing from east to west. So they're blowing from this direction to that direction. And because this is a southern hemisphere, the wind doesn't move exactly with the water. The water doesn't move exactly in the same direction as the wind. The path of the water is deflected to the right, and so the water is moving in this direction. Because the water is moving away from the coast, to replace this water from a depth flows up and upwells along the coast. So the water is flowing up towards the surface here to replace the water that the wind is driving away from the coast. And this upwelling brings cold, nutrient-rich water to the surface. And so we have cooler water, not only because of the eastern boundary current, but because of the upwelling that is occurring here. And the upwelling is bringing very nutrient-rich water. Where here we have the winds blowing this way, which is going to cause some downwelling, and plus we have very warm water, so we expect very nutrient-poor water to be on the east coast of South Africa. So let's look at the biological productivity. So biological productivity of water can be measured by measuring the concentration of chlorophyll in the water. Chlorophyll is a molecule used in photosynthesis. So the more chlorophyll in the water, the more biological productivity, the more phytoplankton you have in the water photosynthesizing. Phytoplankton are important because they're like the vegetation of the ocean. On land, vegetation photosynthesizes, then the herbivores eat the vegetation, the carnivores eat the herbivores. You need that vegetation to support ecosystem. Phytoplankton are the vegetation of the ocean. So small animals eat the phytoplankton, bigger animals eat those animals, all the way up to the large animals. So this biological productivity is very important. And if we look at a yearly average, we can see that there is much higher chlorophyll concentrations on the west coast of South Africa than the east coast. Why is this? Well, because of the easterly winds are driving water away from the coast on the western coast, forcing an upwelling along the coast. And that upwelling brings cold, nutrient-rich water, where the easterly winds on this side are driving water towards the coast, forcing a downwelling. And so you bring the nutrient-poor water over here towards the coastline, and so we have very little biological productivity on the east coast of Africa. Now remember, these waters over here are so deficient in life because the sea surface temperature is very warm, and because of that, there is a large thermocline, so there's a drastic decrease in temperature with depth. And because of the large thermocline, there's a large pycnocline, a drastic increase in density with depth. And that large pycnocline causes the water to layer or stratify, so there's no vertical mixing, and so the surface water becomes depleted of nutrients, and with no nutrients, there can be no photosynthesis. And so these are very, very nutrient depleted warm surface waters, and so there's very little biological productivity. Okay, but over here, and so there's very little biological productivity here, but the difference is there's an upwelling being driven by wind moving water away from the coast, and that upwelling brings nutrient-rich water to the surface. Now if we zoom out, we can see that the water that we would expect to be the most stratified, the waters at the equator, where we expect the water to be the warmest, we actually see biological productivity. So if the water is supposed to be so warm here, and therefore so stratified, how are we getting nutrients to the surface for this biological productivity? Well, the answer is the easterly winds, they converge. So the easterlies from the north, they flow from the west to the east, west to the east, west to the east, and westerlies in the southern hemisphere flow from east to west, east to west, east to west, and they're converging along this line. This is the ITCZ. Not only do they drive water from east to west, but the easterlies in the northern hemisphere drive a small amount of water to the north, and the easterlies in the southern hemisphere drive a small amount of water to the south. And so they're actually driving water away from the ITCZ. And to replace that water that's being driven away, water from depth rises towards the surface. And so the convergence of the easterly winds at the ITCZ drives water away from the ITCZ, inducing an upwelling, bringing cold, nutrient-rich water to the surface. And so the reason why we have biological productivity here is because of the upwelling driven by the convergence of the easterly winds. And we can see that also occurring here. This is an upwelling driven by the convergence of the easterly winds. And so that explains this biological productivity, this line of biological productivity that runs along roughly the equator. Now it will vary with year during the summer if we look at a monthly average. So this is September. If we go to, say, summer, it should be a little bit north, 0 at 1 degree, a little bit north of the equator. And if we go to the winter, it should be a little bit south of the equator because the ITCZ is in the south. And yep, here we are at negative, we're slightly south of the equator. So yes, the ITCZ migrates north and south of the equator through the summer and winter, but if we look at a yearly average, it should be pretty much right on the equator. And remember, we have a lot of biological productivity up here because the surface water is more uniform in temperature compared to the deep water, so there's not a large thermocline, therefore not a large pycnocline, so there's more vertical mixing in the water. And here we don't see the same phenomenon in South America as we do in Africa, because though there is an upwelling here, there's also large rivers dumping large amounts of nutrients in the coastal waters on the east coast of South America. And so that's what's stirring all this biological productivity. It's not an upwelling, it's the influx of nutrients from rivers. So here you can see, like, for example, the Amazon River dumping all these nutrients in the water, causing a large amount of biological productivity. So where life exists in the ocean is dependent upon on the properties of water, how water layers itself whenever there's a large thermocline, therefore a large pycnocline. And so that explains the absence of life in open tropical waters. But also, surface, the atmospheric circulation, the winds, which determine ocean circulation, that also influences where life is found in the ocean as well. So as we continue to go through the semester, we learn that all of these systems are interrelated and connected, and they all depend upon one another. And we can really only fully understand our ocean and our planet while taking all of these different systems into consideration at the same time.